three-phase transformer banks, and we have already talked about three-phase circuits. So we've talked about this before already, but we're going to now talk about what happens when we put a load on this three-phase transformer bank. And we're going to review a couple things we already know. And we're going to discuss different types of three-phase transformer connections. You already know the connections, though, from the three-phase circuit chapter. We're going to show some one-line diagrams, schematics, in other words, some single-line diagrams. We're going to calculate values with different loads and different kinds of loads, delta and Y loads. And we're even going to discuss, possibly, if I can remember that long, we're going to discuss a three-phase load and a single-phase load, because in an office, let's say you have a manufacturing plant, and you started out with just machine shops, and you didn't have any office at all, and you're doing your office stuff at home, and suddenly you realize that you're so big now that you can afford to have an office. So you add an office, and you realize, oh darn, I have nothing but three-phase power here, and I don't have 120 in place. So if I center tap this delta, I can get 120 on two phases, but that's really all on one of the three phases. So we're going to talk about that, if I can remember to, that is. We're going to talk about the different connections. Single-phase transformers can be connected to deliver three-phase power, and this allows greater maintenance and replacement options. They're talking about when we have a delta. If one blows out, it's still going to supply three-phase power. It's just going to not be able to supply as much power. We already know that the primary input side of the three-phase transformer can be connected to Y or delta. We've looked at the Y and the delta connections in the past. Secondary can also be connected to Y or delta. So that gives us four choices for the three-phase transformer bank. It can be YY, delta delta, Y delta, and delta Y. Okay. Now here we have a primary Y and a secondary delta. Not a big deal. And here we have a delta Y. And we've talked about some of the considerations of those. Now we want to remember, we've talked about this before, but we want to recall that the terminations have identifications, H1, H2, and H3, and X1, X2, and X3. And so we have a phase A, phase B, and phase C winding on each winding. And remember, the reason that we want to stay in phase is we want to look at what happens from winding to winding, in and out. And because of that, this is our drawing for any three-phase delta setup, because we can wire the three transformers in delta or Y. And we can put in a delta or Y load, and we're going to talk about that momentarily. Okay. Let me stop for a second. All right, so we can have, one of the connections we can have that the other slideshow does not show much is an open delta, and this is an open delta, open delta. You'll notice that it only has two single-phase transformers forming this thing. And we see there are two single-phase transformers coming in here and two single-phase transformers going out. And this could have been three single-phase transformers where one blew out coming in and one blew out going out. Or it could have been an original connection. Now, you know that an open delta is going to only supply 57.7% of the power that it would have as a three-phase closed delta. So you need to be able to look at those calculations and figure out what that means. Now, open delta is not a normal setup, to say the very least. And more commonly, we might have a closed delta supply and an open delta secondary. And again, on the output, you'll notice we only have two transformers, but we still have three outputs. Look at the connections here. We still have three connections. We still have a phase A, a phase B, and a phase C. So we still have three-phase power, we just don't have as much power as if it were a closed delta. All right, now we need to go down one more and look at how we would connect those if we didn't have one of these windings. We'll come back to that in just a second. I want to talk about one more connection, and I don't have the picture in it yet, so we're going to have to pause for a second again, sorry. As I started to say, we also have a center tap delta that's much more common than an open delta, and it's used to supply 120 volt loads on one of the phases, from one of the phases, and we want 120 volt single phase because we've gone from a little industrial plant that only had motors and motor control stuff, and we're suddenly adding a little office. So we need a little bit of single phase 120 volt power, and one of the ways we can get that without buying new transformers, which is a very important factor, is to center tap one of the delta output windings. This is a center tap delta secondary winding where we have 230 volts across each individual winding. So we have 230 volts across each one of these windings. Okay. And in the single winding, we're going to center tap it and take it to ground so that we have 120 volts across each one of these half windings. And that can be a very handy device because we can still supply all of our three-phase loads off the main banks. But we can take our single-phase loads and put it on one single winding. And what does that do? That means one of the transformers is going to have to be larger than the others because the load in the three-phase is going to be completely balanced around the load, right? Each of the phases, that three-phase load is going to be balanced. But this single-phase load is going to be out of balance. So we're going to have one transformer that's larger. If we can figure out which single transformer is carrying that larger load, we want to use a bigger one where that one is, right? Okay, so it becomes very important to be able to figure out which winding is that secondary winding because that one, when we make our transformer bank up, if we know we're going to do this ahead of time, it might be a good idea to have a larger. What happens, generally speaking, is it gets done after the fact, and probably the transformer wasn't being loaded to its maximum load anywhere or nowhere near there, and so it's okay to add a little load to one of the transformers, as long as it's well within its capacity. So we don't want to overload one of the banks or one of the parts of the bank, but we can create single-phase power out of that. And you notice in this one we have a slightly different voltage. We still have 120 volts across the center winding, the center two windings, but on the outside we have 208 instead of 230. So depending on what motor, three-phase motors we have, we can set this up different ways. All right, so let's do a couple of calculations here, and let's look at, in your project, in the lab, you're going to be doing a delta Y delta, a delta, go ahead and write this down, a delta Y delta, a Y delta Y. I'm not really interested in seeing a Y anything or a delta delta anything, so take that off your list. We're not going to do that. Okay, so for our primary and secondary windings of our transformers, we're not going to connect them Y or delta delta. Okay, we're going to go Y delta Y. Y delta is the primary and secondary, and Y is the load. We're going to go delta Y delta where we have a delta load. And just to keep things interesting, we're going to do a center tap delta where we can get some different voltages. And we can have we're going to imbalance the loads. We're going to load one transformer more than the others. We're going to have a single phase load on those also. So won't that be fun? So it'll be a delta, open delta, and then either a delta load or a Y load, your choice. But that's another project that you can do. Okay, so this is set up for what you're going to do. Now what you're going to do in the lab is you're going to do what we're about to do. What you do, whenever you do these transformer problems, is you start out at the top and work your way down to the bottom with voltages. You're going to go, what voltage do I have coming in the primary line? What do I have in the primary phase? What do I have in the secondary phase? What do I have in the secondary line? Because the line is what's going to go down to the load. So then we're going to look at the line coming into the load, and then we need to look at what happens in each phase, because we need to do what, when we're doing calculations, stay in phase. We want to stay in phase to do our calculation. And once we have our calculation for our phase, then we can go back to our line and our load, and then from that we can go back to our line and our output of our transformer. Then we can look at the phase of the output of the transformer. Then we can look at the, and we're looking at the currents as we go back up. So we get the voltages going down to find out what voltages across the phase of the load. And then we're going to find the current, because we'll know the impedance of the load. And in the past, we've only talked about pure resistive loads. And for simplicity, that's easier to look at, right? But what we want to do is we want to look at what would happen if we had a motor on this thing. We would have an inductance and a resistance. We'd have a triangle problem, right? And so we're going to start looking at how we calculate the triangle in that point and find out what happens there and start taking that information back up. Okay? But first we want to be able to get the voltages going down and then get our currents and start going back up. So let's do a, what did I say we're going to do first? Delta Y delta? Yes. Okay, let's do a delta Y delta. Okay? Here we have our drawing. We're going to connect our primaries as a delta. So we're going to tie these two together. Remember that the delta looks like this, and we're going to wire it like this. And so we want to wire from corner to corner, and we're going to tie the primaries into where it comes in. Lost my drawings, that's okay. And this is going to, that's phase A coming in. This is phase B coming in. This is phase C coming in. And so now we have the input wired as a delta. Now we want to have the output go out as a Y. So we know that we're going to tie the right side of each transformer to a grounded conductor, and we generally call that a neutral. And we're going to have phase A coming out of here, phase B coming out of here, and phase C coming out of here. And I said we're going to have a delta Y delta, right? So we're going to have a delta load, and for simplicity, again, just this once, we're going to say that it's purely resistive, and I really ought to put that down as a resistive load, but I can't resist drawing a winding. So we have phase A, phase B, phase C. And now, let's take a voltage, and what voltage we have coming in on our primary? 480 volts. Okay, if it's a delta input, a quick review of our delta rules. What's common in delta? Voltage. And phase current times square root of 3 is line current. Remember that? Okay, so if that's true, then if we have 480 on the line, then we have a 480 volt primary. And what step-down ratio do you think we ought to have? 4 to 1? 2 to 1. Let's go 2 to 1. 2 to 1, step down. So our secondary voltage would be what? 240. Okay, now that is a phase, right? That's a phase, but this is a Y output. Remember, this is a Y output. And if that's true, and we have 240 volts here, what is our phase voltage? 240 times square root of 3 is 415 volts. Thank you. Okay, so that means that we have 415 volts on the phase of the load. Is that correct? Correct? Because it's the phase voltage that goes down to our load, right? I mean the line voltage, sorry. The line voltage is all the same in a delta, but our our line voltage on our output is 415 volts, and that's what's connecting to our load input. We have a line, 415 volts, and since it's delta load, what is the phase voltage? 415 volts. Now, we need to know what our resistance, we'd like to do our impedance now, but we're not ready for that just yet. But if that's true, what's our resistance here? What's the resistance of our load? Pick one. 8 ohms? All right. If that's true, if my voltage is 415 volts and I divide that by 8, what do I find? Say again? Okay, now that is what? 51.8 amps is a phase current. Now, in a delta load, what is all the same? The voltage is the same. The current is not. If that's our phase current, what's our line current? Donald? 89.8. 89 point what? 8. Thank you. So we have 89.8 amps on our line at the load, right? So what does that mean for our line and our output? That's our line current on our Y. Everybody agree with that? And in Y, the currents are the same. So what's our current right here on our secondary winding? 89.8 amps. Just a 2-to-1 step down, right? Yeah. So what is our current up here? This times this, 240 times 89.8 has to be 480 times the current in the primary, right? So it's half this. Everybody agree with that? What is half of 89.8? 44.9. Thank you. 44.9. That is our primary phase current. All right? So what is my primary line current? In delta, the voltage is all the same, but the phase and the line current are different in what way? Phase times square root of 3 is line. So 44.9 times square root of 3. 77.8. Point what? 8. Excellent. That is our primary line current. And that is how we do that calculation. Okay? We did every step. We went down finding the voltage, right? Then we found the current in the load phase. Would it matter if we had a Y load down here? No, we would still find the phase load current, right? And then we'd start going back up. So that's the process. Now, other people will tell you to go round in a wheel where you start going, but it's the same thing. Other people have a method where they say you're going in a circle and you're coming back to the beginning point. Well, that's true, except this is our halfway point at the middle of the circle. All right? Everybody clear on that? Okay, the rule we're always following here is that the number of windings, oh, I just lost my writing space. Number in the, I can't, that's not enough room. I'm going to just add a slide. Hang on one second. All right, so the rule we're always following here, just as a reminder, is the number of windings in the primary. Why are we having trouble with this? Or the number in the secondary is equal to voltage in the primary. Come on. Why is it not working? There. No, it's still not working. Okay, and remember that the voltage ratio and the windings ratio are the same fraction, just different scales. And the current ratio is the inverse function. So when we write the current, why is it not working? Notice that the secondary is on top in the last one. Okay, so it's number in the primary over the number in the secondary is equal to the primary voltage over the secondary voltage, which is equal to, we flip the fraction over and it's still the same numeric fraction, different scale, current in the secondary over the current in the primary. Okay, and we use that when we're going in and coming out of this calculation. Okay. Let me hit pause for just a second. All right, let's now look at a Y delta Y, and we're going to say that we have 575 volts coming in as our primary line voltage. And let's pick a resistance before we start, and we're going to suppose that it's all resistive just to keep it nice and simple for the moment. And what was our resistance last time? 8 ohms. 8 ohms. All right, let's call it 10 ohms. How's that? Nice even numbers like that. Okay, so now if we have 575 volts primary Y line voltage, line voltage, what is our phase voltage? 331. Thank you, 331 volts. Because we're going to divide 575 by the square root of 3, right? Okay, so we have 331 volts. Now let's go to our drawing. Come on. Okay. Let's go back to our drawing, and we have Y. And we have Y coming in. delta going out. And we're going to say that we have a Y load this time.
Yes, that's how.
And we have, what was our resistance?
10 ohms.
10 ohms. Okay, and we have 575 as our primary, and our phase voltage was what?
331.9.
331?
331.98.
All right, 332, I can go with that. 332 volts. And again, we have a Y going out. Let's go 2 to 1. Keep it simple. Okay, so if it's 2 to 1, what is my secondary phase voltage? Half of 331, 332.
165. Wait, you said 166.
166 volts. You rounded a little bit up. That's okay. That's fine. Okay. And we have a delta coming out of here, right? And we have a Y load. We have A, B, C. And so my voltage across the phase of the load is 166 volts, right? So what is my phase? My line voltage across the load is 166 volts. I think I said that wrong, but the phase voltage coming to the load, did it again. The line voltage coming to the load is 166 volts. So what is my phase voltage? Because it's square root of 3 of that, right? Divide that by square root of 3.
287.5.
95 point what? 84. Okay, 95.84 volts. Let's go over here and do our power, voltage, current, impedance. And it's totally resistive, and we got 10 ohms, and we have 95.8. So my current's going to be 9.58, right? Okay, so if I have 9.58 amps in my phase, now what's all the same in Y? Current. So that means my phase current is 9.58 amps. Everybody agree with that?
Is that your secondary phase current?
That's my secondary, no, that's my load phase current. Load phase current. Okay? My load phase current. Now, if that's my load phase current, what does that mean to my transformer delta output? That's my line. Okay, so my line current in that delta is 9.58. But in delta, the currents are not the same. What is my phase current in that delta? If my line current is 9.58, what is my phase current?
5.53.
Say again?
5.53.
5.53, because we divided this 9.58 by the square root of 3, right? Yes?
Yes.
Okay. And we find that we have 5.53 amps. Is that correct? Everybody agree with that? Okay, so what is that, my 5.53? That is my secondary phase current in my transformer, right? So now, as I look up here, it's a 2 to 1 step down, so I know my phase current in my primary is half that, right? Has to be. So half of 5.53.
2.765.
So that incoming power is 575 volts at 332. It's one more time. My primary phase totals are 332 volts at 2.765 amps, right? And in a Y, what is the same? Current. So my current across this line is the same, 2.765 across the line. Nice and simple, right? As long as you follow the steps carefully. It's not that hard. You just have to be careful going down and looking at what is this, what is that, how do they work together, what's this one, what's that one. Get down to your voltage and your phase and then start going back up with the current, right? Piece of cake, right? Until we do an open delta or we do a center tap delta, right? Because then we're going to have, our book, by the way, does talk about how to calculate the loads when it's a center tap delta, because all we do is we have more single phase load on one of the transformers, right? So one of the transformers is going to have to deliver more power. That's all there is to it. So that's pretty simple. Now, if we want to calculate the total power, especially, well, we'll talk about that in a second. But if we want to, where our load is the same on all three phases, and that's a caveat, right? With that caveat, when they're all the same, then we can find the total power of a three-phase bank by looking at the phase totals or the line totals. So if we look at this and we multiply, now what is the formula? Let me write this. There's hardly any room in here, but let me write this up here. I think I can get it in here. And power total, and this is apparent power, by the way, is phase voltage. Actually, that ought to be E sub T, right? Times current phase times 3 is our total power. Everybody agree with that? Anybody agree with that? Anybody remember that? And if we want to know the true power, we just multiply this times the power factor, right? And that becomes true power. Okay? That becomes true power. But we don't want to talk about true power just yet. Okay? We just want to talk about apparent power for the moment. Now, if we're talking about line totals, we could say that our apparent power is equal to the line voltage times the line current times square root of 3. And if we want to turn that into our true power, we just multiply times what? Power factor. But we're going to leave it at this. So there's your reminder of how to find your total powers. That was from the previous chapter on three-phase circuits. But there we have a summation of how to find the total power. Now, what if one of these transformers is larger than the others? And it's delivering more power than the other? Then we have to add, it's very simple. We take the phase voltage times the phase current, and that's the power in that one transformer, right? That's the apparent power in that one transformer, right? We add that to the phase voltage times the phase current and another transformer, and the phase voltage times the phase current and another transformer, and then we just add them up. If they're not the same, you have to stay in phase. You cannot do line. You can, but it's going to be a little more difficult because then you're going to have phase voltage times, line voltage times line current times square root of 3. It's just going to be no fun at all. Yes, sir. All right, now on these problems, you also need to do calculations with the open delta, because in the lab, you're going to have an opportunity to do a delta, open delta with a Y load, either 250 ohms or 600 ohms, and you're going to need to do the calculations ahead of time and come up with the right numbers, because what you do first part of each one of these projects is to do a drawing of all the windings and the load and show all your calculations for everything, and then highlight your voltage is going down and your current's coming back up, and then you're going to show it with a real transformer connected, doing the real thing. And they're 2-to-1 step downs all the way, so we're doing the same exact. So there we go. We're going to call it a day, and that's the end of that. Thank you.